My name is Kennon, and I'm a senior working in Elizabeth Brandon's Developing Minds lab. I, alongside my partner, Natalie Driscoll, will be presenting our research on children's area perception. Perceiving size should be easy. Virtually every task that we complete throughout the day depends in some way on accurately perceiving the sizes of objects around us. When we're picking up a coffee mug, we must know how large it is in order to grasp it properly. When picking out food at the grocery store, we need to know how much to add to our cart. And when placing objects around a table, we have to allow space for all of them. Surprisingly, despite the commonality of size perception tasks, humans are remarkably poor at this ability. However, little research has been done about how humans, and specifically children, actually comprehend size and area comparisons. Why is it that size perception can be so easily distorted if this is such a foundational and constantly used ability? Here, we explore the developmental origins of size perception in order to better understand why these distortions arise in the first place. That said, there are a few theories concerning area perception that exist in the literature. The most prominent are veridical models, scaling models, and additive area models. We specifically designed our stimuli to test key aspects of those models. We'll have children complete simplistic yet intriguingly tricky size perception tasks. We have several different stimuli that we will present to children, asking them to judge their size relative to other shapes of either greater or equivalent area. We have 13 different pairs of stimuli. Each pair attempts to test and validify different heuristics. Some of the stimuli differ on vertical height, horizontal length, and total area, etc. The goal of each example is to properly address what part children are taking into consideration when answering their size comparisons. For example, one of the stimuli compares a 4x4 square to a 6x2 rectangle. In this example, mathematically, the square has greater area. However, the rectangle is significantly taller than its counterpart. If children are simply looking at the longest side to make their area assumptions, they would indicate the rectangle as the largest. If they were to use additive area or true mathematical area, they would answer the square. Through this study, it is our hope that we gain a better understanding of area perception's development in children throughout the early elementary school years. Comprehending how children perceive areas would speak to both the visual and cognitive development of children more generally. Understanding area perception is also necessary in order to measure and change area in other studies of quantity perception. Without understanding the basic underlying heuristics, it is impossible to manipulate area to test for the perception of quantity, as area perception could be a confounding variable without properly manipulating it. So that is why we did our test to decide how children perceive area.